Welcome to Chapter 4, Section 1, Related Rates. In this section, we are going to put together our rules of differentiation and implicit differentiation to solve some applied problems here. So let's start off with a simple one. Let's say we have a spherical balloon and the radius is changing at a rate of 2 inches per second. And we want to know how quickly the volume of the balloon changes with respect to time when the radius is 10 inches. Now, in previous sections, we've looked at this using the chain rule, saying that, well, the rate of change of the volume with respect to time is going to equal the rate of change of the volume with respect to the radius times the rate of change of the radius time with respect to time, which that's still true in this case. And in fact, we could solve this using the same method, but we're going to ignore this method here and use our related rates problem to help us apply it to more difficult problems a little later on. So the chain method would still work here, and in fact, you're going to find that our result is going to be pretty much identical, but we're just going to look at things slightly differently. So let's start off with the formula for volume of a sphere, which is 4/3 pi r cubed. And we want to take a derivative of this with respect to time, because that's our goal here. We want to find the rate at which volume is changing with respect to time, and we're just going to evaluate it when r is equal to 10. Okay, well, when we take the derivative of volume with respect to time is just our dv dt, and when we take a derivative of this right half, we get these constants out front, which we're going to multiply by 3, so we end up getting 4 pi r squared dr dt. Okay, and this is where the chain rule pops out. We're taking a derivative with respect to r, but we need to take the derivative of r with respect to t. Okay, and we look, and we know 4 pi because that's a constant. We know r because we're given 10 inches, that's when we want to evaluate, and we know dr dt is simply 2 inches per second. So to evaluate this at evaluate this at r equals 10, we simply just plug in. So the rate of change of the volume with respect to time when the radius is 10 inches is 4 times pi times 10 squared times 2. And so when you multiply all these together, 10 squared is 100, times 2 is 200, times 4 is 800. So this is simply 800 pi, and what are the units here? Inches per second. Okay? And if you wanted to put that as a decimal, you could. It would be around 2,400. All right? So let's summarize this into a strategy that we're going to use for all of our related rate problems. And there's 4 basic steps that we're going to follow here when we solve different related rate problems. First, typically we're going to draw a figure and label the quantities that. Now in the previous example I did not draw a figure, but it wasn't entirely necessary because it was just a simple volume problem that we had a formula and we differentiate with respect to time. But in most cases you are going to draw a figure and label the quantities that vary. And then you're going to find an equation that relates the quantity with the unknown rate of change to the quantities whose rates are known. So we need some type of equation that we can relate all of our known and unknown quantities. And then we're going to differentiate both sides of the equation with respect to time, because these are related rates. All of them are going to have some time component in them, and that'll give us the unknown rate of change somewhere. We're going to typically differentiate implicitly, so the rate of change might not pop out and give us an explicit equation, but we can use our algebra skills to find that explicit equation and then evaluate the derivative at the appropriate point. So let's look at an example using this 4-step strategy. So let's say we have a hot air balloon that's rising straight up from a level field, and it's tracked by a rangefinder 500 feet from the liftoff point. So we have a rangefinder right over here, and it's 500 feet from where the balloon lifts off. At the moment, the angle, now we're talking about this angle of elevation right here, theta, is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. So this is telling us d theta dt is 0.14 radians per minute. And we want to know how fast is the balloon rising at that moment. So really what we're looking for is if it's rising, and we call this height h, we're looking for dH dt. That's what we want to know. So we need an equation that relates our known and unknown. So we have a right triangle here, knowing that this is a right angle. It's a level field. It's rising straight up, so it's perpendicular to the ground. And we want to look at, well, how is our angle h and 500 all related? That's going to be tangent of theta is equal to h over 500. That's our equation right here that we're going to use. So let's rewrite the equation and say that it's h equals 500 tangent of theta. And now let's take the derivative with respect to time. The next step is take the derivative with respect to time of both sides. So that gives us dH dt is equal to 500 times secant squared of theta times d theta dt. And so at this point, all we have to do is evaluate the function at the appropriate point. What is that appropriate point? Well, that's when d theta dt is 0.14, and that's when theta is equal to pi over 4, and that gives us all the variables that we need, so we plug that in, and you get 140 feet per minute. So this tells us the rate at which this balloon is rising at that moment. Now, where did the 140 come from? Well, plug in pi over 4 into secant squared, and you get radical 2 squared, which is just 2, times 500, which is 1,000 multiplied by 0.14, and so you get 140 feet per minute.